Right now, as you read these words, there might be another version of you in a parallel universe making a completely different choice. Perhaps in that universe, you decided not to watch this video. Maybe there is another universe where you became a professional athlete instead of whatever path you've chosen in this reality. According to some of our most successful theories in physics, these parallel universes aren't just science fiction. They read mathematical necessities that emerge from the fundamental laws governing quantum mechanics and cosmic inflation. We thought our universe was everything that exists, the totality of space, time, matter, and energy. We were spectacularly wrong. Multiple independent lines of theoretical development in modern physics, from quantum mechanics to cosmic inflation to string theory, all point toward the same startling conclusion. Our observable universe is just one bubble in an infinite multiverse containing countless other realities with different physical laws, different histories, and different possibilities for life and consciousness. But here's what makes this revelation revolutionary. We're no longer limited to pure speculation. Cutting-edge experiments and observations are bringing us tantalizingly close to detecting direct evidence for parallel universes. The search for parallel universe detection represents the ultimate frontier in experimental physics, requiring us to push the boundaries of what is technically possible while developing entirely new approaches to studying reality itself. From quantum interference experiments that might reveal parallel quantum histories to cosmic observations that could detect collisions between universe bubbles, scientists are developing ingenious methods to test what was once considered pure philosophy. Tonight we're going to explore 12 revolutionary approaches that could provide the first concrete evidence for parallel universes, examine why multiple theoretical frameworks predict their existence, and discover how advanced civilizations, including, potentially, our own, might develop the technology to peek beyond the boundaries of our cosmic bubble. Dr. Max Tegmark from MIT has outlined 4 distinct levels of parallel universes, each requiring different detection strategies and offering different insights into the nature of reality. Level I involves regions beyond our cosmic horizon where space continues, but with different arrangements of matter. Level 2 includes bubble universes with different physical constants created during cosmic inflation. Level 3 emerges from quantum mechanics and the many worlds interpretation. Level 4 encompasses all possible mathematical structures as physical realities. What makes parallel universe detection so challenging is that, by definition, these other realities are normally isolated from our own. However, several theoretical mechanisms predict subtle ways that information or effects from parallel universes could leak into our observable reality. These interdimensional signals might take the form of gravitational wave signatures, cosmic microwave background patterns, quantum entanglement anomalies, or even direct particle interactions at extremely high energies. The theoretical foundation for parallel universes emerged from attempts to solve fundamental puzzles in physics and cosmology. Quantum mechanics appears to require that all possible outcomes of quantum events occur simultaneously in parallel realities. Cosmic inflation theory suggests that our Big Bang was just one of countless expansion events creating separate universe bubbles throughout higher dimensional space. String theory indicates that our universe might be a 3-dimensional slice through higher dimensional spaces containing other 3-dimensional universes. Consider this mind-bending possibility. Every quantum measurement you've ever observed, from radioactive decay events to photon detection in your retina, might have generated parallel branches of reality where different outcomes occurred. The version of you reading these words represents just one path through an exponentially branching tree of quantum possibilities, with parallel versions exploring every alternative timeline simultaneously. The detection challenges are staggering. Parallel universes, if they exist, operate with such minimal interaction with our reality that their effects might be detectable only through the most sensitive experiments ever conceived. We need technologies capable of measuring gravitational fields with precision, approaching the fundamental quantum limits. Quantum systems isolated enough to detect interference from parallel quantum states and cosmic observations, sensitive enough to identify the signatures of universe collisions that occurred billions of years ago. But recent theoretical breakthroughs suggest that parallel universe detection might be closer than we imagine. Advances in quantum computing are creating systems that might naturally access parallel quantum realities during their calculations. Gravitational wave observatories are approaching sensitivities that could detect exotic spacetime distortions caused by parallel universe interactions. Cosmic survey telescopes are mapping the universe with precision sufficient to identify subtle patterns that might indicate influences from other realities. Dr. Carroll from Caltech has argued that the many worlds interpretation of quantum mechanics makes specific, testable predictions about the behavior of quantum systems. If parallel quantum realities exist, they should interfere with our reality in measurable ways that create subtle but detectable signatures in carefully designed experiments. These quantum interference effects might provide the first direct evidence for the existence of parallel quantum branches. The cosmic implications are equally profound. If cosmic inflation created multiple universe bubbles, these bubbles should occasionally collide, leaving distinctive signatures in the cosmic microwave background radiation that we can detect using advanced space-based observatories. If our universe exists within higher dimensional spaces, gravitational effects might leak between parallel universes in ways that could be detected through precision measurements of gravitational fields. The technological requirements for parallel universe detection are pushing us to develop capabilities that seemed impossible just decades ago. Quantum isolation chambers approaching absolute zero temperature gravitational wave detectors, with arm lengths measured in light years and cosmic observation platforms positioned at the edge of the solar system, all represent technologies that could provide the sensitivity needed to detect interdimensional effects. Perhaps most remarkably, the search for parallel universes is revealing deep connections between the largest and smallest scales of physics. The quantum mechanical processes that might create parallel realities operate at subatomic scales, yet their consequences could influence cosmic structure formation across billions of light years. Understanding parallel universes requires bridging quantum mechanics and cosmology in ways that are revolutionizing both fields. If you're fascinated by experiments that could reveal hidden layers of reality beyond our direct perception, subscribe and hit thumbs up. And here is a question that will transform how you think about existence itself. If every quantum measurement creates parallel branches of reality, and if advanced civilizations might develop technology to detect these branches, what would it mean to make contact with parallel versions of ourselves? Comment below with your thoughts. I'll pin the most mind-expanding answer. The search for parallel universes represents more than just an exotic scientific quest. It is humanity's attempt to understand whether our reality is unique or whether existence itself operates on scales and through mechanisms far grander than we've ever conceived. The detection methods we're about to explore could prove that consciousness, choice, and cosmic evolution operate simultaneously across infinite parallel realities, or they could reveal new physics even stranger than the multiverse theories that inspired them. Now let us begin our journey into the cutting-edge science that might soon provide the first concrete evidence for parallel universes, exploring 12 revolutionary detection methods that could transform our understanding of reality itself and our place within the vast cosmos of infinite possibilities. Chapter 1. Quantum Tunneling. Quantum tunneling represents our first and potentially most promising avenue for detecting parallel universes through direct experimental verification of quantum mechanical predictions that particles can exist in multiple states simultaneously until measurement forces them to choose a single outcome. The many worlds interpretation suggests that rather than collapsing into a single state, quantum systems branch into parallel realities where each possible outcome occurs. Detecting this branching could provide the first direct evidence that parallel quantum universes actually exist. The theoretical foundation for quantum tunneling detection of parallel universes emerged from work by physicist David Deutsch at Oxford University, who showed that quantum computers naturally access parallel quantum realities during their calculations. When a quantum computer performs a calculation involving superposed quantum states, it effectively explores all possible computational paths simultaneously across parallel quantum branches. The final result represents an interference pattern between calculations performed in parallel realities. Dr. Seth Lloyd from MIT has developed experimental protocols that could detect quantum interference between parallel branches by creating quantum systems that remain in superposition for extended periods while interacting with carefully controlled environments. These experiments involve isolating quantum systems at temperatures approaching absolute zero and magnetic field strengths that eliminate environmental decoherence, the process that normally destroys quantum superposition, by entangling quantum systems with their environments. The key insight is that if parallel quantum realities exist, they should create subtle interference effects that slightly modify the probability distributions of quantum measurement outcomes. These modifications would be extraordinarily small, perhaps detectable only in one measurement out of millions, but they would represent smoking gun evidence for the existence of parallel quantum branches that occasionally interfere with our reality. Professor Max Tegmark has calculated that detecting quantum interference from parallel universes would require quantum systems with coherence times measured in hours rather than the microseconds typical of current quantum experiments. Achieving such long coherence times requires isolation chambers that approach perfect vacuum conditions, eliminate all electromagnetic field fluctuations, and operate at temperatures within thousandths of a degree above absolute zero. The experimental setup involves creating quantum systems in carefully prepared superposition states, allowing them to evolve for extended periods while remaining isolated from environmental decoherence, then performing precise measurements to detect tiny deviations from standard quantum mechanical predictions. These deviations would manifest as subtle correlations between measurement outcomes that shouldn't exist if our universe represents the only branch of quantum reality. Recent advances in quantum error correction have brought these experiments within reach of current technology. Dr. John Preskill from Caltech has shown that quantum error correction protocols can maintain quantum coherence for arbitrarily long periods by continuously detecting and correcting quantum errors without destroying the quantum superposition. These techniques could create quantum systems stable enough to detect interference from parallel quantum branches. The detection signatures would involve statistical patterns in quantum measurement outcomes that violate standard quantum mechanical predictions in specific ways predicted by many worlds theory. For example, if parallel quantum branches occasionally interfere with our branch, we might observe correlations between spatially separated quantum measurements that exceed the limits imposed by quantum entanglement in a single universe scenario. Dr. Anton Zeilinger from the University of Vienna has designed quantum interference experiments using photons that travel through sophisticated interferometer systems designed to amplify quantum effects from parallel realities. These experiments involve creating photon superposition states that explore multiple paths through the interferometer simultaneously, with detection systems sensitive enough to identify minute phase shifts that might result from interference with photons traveling through parallel quantum branches. The technological challenges are formidable. Detecting quantum tunneling signatures from parallel universes requires measurement, precision approaching the fundamental limits imposed by quantum uncertainty principles. The detection systems must be sensitive enough to identify individual quantum events while maintaining statistical accuracy over millions of measurements to extract meaningful signals from quantum noise. Professor Nicolas Guézin from the University of Geneva has investigated whether quantum entanglement experiments might reveal evidence for parallel universes by detecting correlations that exceed what is possible within a single quantum branch. If parallel realities exist, entangled particles might maintain correlations not just with their partners in our universe, but also with parallel versions of themselves in other quantum branches. The implications extend beyond fundamental physics to practical applications in quantum computing and cryptography. If quantum computers can access parallel realities during their calculations, understanding this process might enable quantum algorithms that solve problems by distributing calculations across multiple parallel universes. Such parallel universe computing could provide exponential speedups for certain types of calculations by harnessing the computational power of infinite parallel realities. Modern quantum experiments are approaching the sensitivity needed to detect these subtle effects. The development of quantum sensors capable of detecting individual quantum events with near-perfect efficiency, combined with quantum error correction techniques that maintain coherence for extended periods, is creating experimental platforms where parallel universe signatures might become detectable. Dr. Christopher Monroe from the University of Maryland has created trapped ion quantum systems that maintain quantum superposition for record-breaking periods while remaining sensitive to external quantum influences. These systems could serve as quantum telescopes that detect subtle influences from parallel quantum branches by measuring tiny deviations from expected quantum behavior. The statistical analysis required to extract parallel universe signatures from quantum noise involves sophisticated techniques borrowed from particle physics experiments. Researchers must analyze millions of quantum measurements to identify patterns that deviate from single universe predictions by amounts smaller than typical experimental uncertainties. Advanced machine learning algorithms are being developed to identify these subtle signatures automatically. Professor Daniel Gottsman from the Institute for Quantum Computing has outlined theoretical frameworks for distinguishing genuine parallel universe effects from experimental artifacts or unknown systematic errors. These frameworks require multiple independent experimental approaches that would all show consistent signatures if parallel quantum realities exist, but would show uncorrelated results if the effects arise from experimental problems. The quantum tunneling approach to parallel universe detection represents the intersection of fundamental physics and cutting-edge technology. Success would not only confirm the existence of parallel realities, but would also validate quantum mechanical descriptions of reality that extend far beyond our direct experience. The experiments currently being developed could provide within the next decade the first concrete evidence that our universe is just one branch of an infinite quantum multiverse. The search for quantum signatures of parallel universes is also revealing new approaches to quantum computing and information processing that exploit the potential existence of parallel quantum realities. If quantum systems can access information from parallel branches, this could enable new types of quantum algorithms that solve problems by integrating results from calculations performed across multiple realities simultaneously. As quantum technology continues advancing toward the sensitivity required for parallel universe detection, we approach a watershed moment in physics where abstract theoretical concepts might become experimentally accessible realities. The quantum tunneling experiments being developed today could transform our understanding of the nature of existence itself by revealing that every quantum measurement creates new branches of reality that continue existing in parallel to our own observed outcomes. Chapter 2. Gravitational Waves. Gravitational wave detection represents one of the most promising pathways for discovering evidence of parallel universes through the search for exotic space-time distortions that could result from interactions between universe bubbles in higher dimensional space. Unlike quantum tunneling experiments that probe parallel quantum realities, gravitational wave searches for parallel universes focus on cosmic scale phenomena that might leave detectable signatures in the fabric of spacetime itself. The theoretical foundation for gravitational wave signatures of parallel universes emerged from work on cosmic inflation and extra-dimensional physics. Professor Lisa Randall from Harvard University has shown that if our universe exists as a three-dimensional brane within higher dimensional space, gravitational effects from parallel universe branes could create detectable distortions in spacetime that propagate as gravitational waves with characteristics unlike any sources within our own universe. Dr. Kip Thorne from Caltech, one of the founders of gravitational wave astronomy, has outlined how parallel universe interactions might generate gravitational waves with distinctive signatures, extremely long wavelengths corresponding to the size scale of universe bubbles, unusual polarization patterns that don't match any known astrophysical sources, and arrival directions that don't correlate with any visible cosmic structures. The detection challenge involves identifying gravitational wave signals that originate from beyond our universe as boundaries, while distinguishing these exotic signatures from the increasingly diverse catalog of astrophysical gravitational wave sources. Current gravitational wave observatories like LIGO and Virgo have revolutionized astronomy by detecting signals from black hole mergers, neutron star collisions, and other extreme cosmic events. But parallel universe signals would require even greater sensitivity and entirely new analysis techniques. Professor Alessandra Bornano from the Max Planck Institute has developed theoretical models for how universe bubble collisions during cosmic inflation could generate gravitational waves that propagate across higher dimensional space and enter our observable universe. These collision signatures would appear as burst-like gravitational wave events with durations much longer than typical astrophysical sources and amplitudes that depend on the collision, angle, and relative velocities of the colliding universe bubbles. The experimental approach involves using networks of gravitational wave detectors to search for correlated signals that match theoretical predictions for parallel universe interactions. Unlike astrophysical sources that generate gravitational waves through accelerating masses within our universe, parallel universe signals would originate from space-time distortions that affect our entire cosmic region simultaneously, creating distinctive correlation patterns between detectors separated by continental distances. Dr. Bangalore Sathya Prakash from Cardiff University has designed data analysis algorithms specifically for detecting parallel universe gravitational wave signatures. These algorithms search for gravitational wave patterns that violate the assumption that sources exist within our three-dimensional space, looking instead for signals that suggest propagation through high-dimensional geometries or interaction with gravitational fields from parallel cosmic regions. The sensitivity requirements for detecting parallel universe gravitational waves push current technology to its absolute limits and beyond. Future gravitational wave observatories, like the proposed Cosmic Explorer, would have arm lengths of 40 kilometers compared to LIGO's 4 kilometers, providing sensitivity improvements that could make previously undetectable parallel universe signals accessible to observation. Space-based gravitational wave detectors represent the ultimate frontier for parallel universe searches. The proposed LISA mission would create a gravitational wave observatory with arm lengths of 5 million kilometers, sensitive to gravitational wave frequencies that could reveal signatures of universe bubble interactions occurring on cosmic scales. Dr. Karsten Dansman from the Albert Einstein Institute has calculated that LISA could detect gravitational wave signatures from parallel universe interactions that occurred during cosmic inflation, billions of years before our solar system formed. The data analysis challenges for parallel universe gravitational wave detection involve distinguishing genuine interdimensional signals from instrumental noise, astrophysical sources, and unknown systematic effects. Advanced machine learning algorithms are being developed to identify patterns in gravitational wave data that match theoretical predictions for parallel universe signatures while rejecting false alarms from conventional sources. Professor Bernard Schutz from Cardiff University has explored how gravitational wave searches for parallel universes could be combined with cosmic microwave background observations to provide independent confirmation of interdimensional effects. If universe bubble interactions create both gravitational wave signatures and temperature patterns in the cosmic microwave background, detecting correlated signals in both data sets would provide compelling evidence for parallel universe interactions. The theoretical predictions for parallel universe gravitational waves depend critically on the specific model of extra-dimensional space and the mechanism for universe bubble interactions. String theory models predict different gravitational wave signatures than models based on brand-new scenarios or theories with warped extra dimensions. This diversity of predictions provides multiple targets for experimental searches while also creating challenges for data interpretation. Dr. Elie Kavitz from Ben Gurion University has developed Bayesian analysis frameworks for comparing different theoretical models of parallel universe gravitational waves against observational data. These frameworks can determine which theoretical models best explain any detected signals while quantifying the statistical significance of evidence. FOR parallel universe interactions versus conventional astrophysical explanations. The search for parallel universe gravitational waves also involves looking for subtle modifications to gravitational wave propagation that might result from interactions with extra-dimensional geometry. If our universe exists within higher dimensional space, gravitational waves might experience tiny modifications to their speed of propagation or polarization characteristics that could be detected through precision measurements of well-understood astrophysical sources. Professor Tessa Baker from Queen Mary University of London has investigated how gravitational waves from black hole mergers might carry information about extra-dimensional physics that could reveal the existence of parallel universes. By precisely measuring the propagation characteristics of gravitational waves from sources at various cosmic distances, researchers might detect systematic deviations that indicate gravitational interaction with parallel cosmic structures. Advanced data analysis techniques are being developed to search for gravitational wave signatures that could only arise from parallel universe interactions. These include searches for gravitational wave memory effects that persist long after the passage of the wave, unusual dispersion relationships that suggest propagation through higher dimensional space, and correlation patterns between gravitational wave signals and other cosmic observations that might indicate interdimensional influences. The upcoming generation of gravitational wave detectors will provide unprecedented sensitivity to exotic gravitational wave sources. The proposed Einstein telescope in Europe and Cosmic Explorer in the United States would represent thousand-fold improvements in sensitivity compared to current detectors, potentially making parallel universe gravitational wave signatures detectable for the first time in human history. Dr. Valerio Ferroni from Bishop's University has explored how gravitational wave astronomy could reveal information about the geometry of higher dimensional space by analyzing how gravitational waves propagate between parallel universe regions. Different extra-dimensional geometries would create distinctive signatures in gravitational wave propagation that could be distinguished through careful analysis of signals from multiple sources. The integration of gravitational wave observations with other astronomical datasets provides additional opportunities for detecting parallel universe signatures. Correlations between gravitational wave signals, cosmic ray arrival patterns, and electromagnetic observations might reveal interdimensional effects that would be undetectable through any single type of observation. As gravitational wave astronomy continues advancing toward greater sensitivity and broader frequency coverage, the search for parallel universe signatures represents one of the most exciting frontiers in experimental physics. Success would not only confirm theoretical predictions about the multiverse, but would open entirely new windows for studying the large-scale structure of higher-dimensional space and the cosmic processes that govern the birth and evolution of universe bubbles throughout infinite parallel realities. Chapter 3. Cosmic Background. The cosmic microwave background radiation. The afterglow of the Big Bang that fills all of space might contain hidden signatures of parallel universe interactions that could be detected through advanced analysis techniques and future space-based observatories. This ancient light, which has traveled through space for nearly 14 billion years, could carry information about collisions between universe bubbles, influences from extra-dimensional space, and other interdimensional phenomena that left permanent imprints on the cosmic background. The theoretical foundation for cosmic microwave background signatures of parallel universes emerged from cosmic inflation theory and its prediction that our Big Bang was just one of countless expansion events, creating separate universe bubbles throughout higher dimensional space. Professor Alan Guth from MIT, who developed inflation theory, has shown that when these universe bubbles occasionally collide, they should create distinctive temperature patterns in the cosmic microwave background that can be distinguished from normal density fluctuations. Dr. Matthew Kleben from New York University has developed detailed theoretical models for how universe bubble collisions would appear in cosmic microwave background observations. These collisions would create circular or elliptical patterns of temperature, enhancement or depression that depend on the collision angle, the relative expansion rates of the colliding universes, and the time since the collision occurred. The signatures would appear as subtle but systematic deviations from the nearly perfect uniformity of the cosmic background. The search for parallel universe signatures in cosmic microwave background data requires analysis techniques that can identify geometric patterns hidden within the tiny temperature fluctuations that characterize this ancient radiation. The Planck space mission, which mapped the cosmic microwave background with unprecedented precision, created datasets containing over 50 million measurements that must be analyzed using sophisticated statistical methods to extract potential interdimensional signatures. Professor Hiranya Paris from University College London has pioneered machine learning approaches to cosmic microwave background analysis that can automatically identify unusual patterns that might indicate parallel universe interactions. These algorithms search for correlations in temperature patterns that match theoretical predictions for universe bubble collisions while rejecting patterns that could arise from conventional astrophysical processes or instrumental effects. The detection challenges involve distinguishing genuine parallel universe signatures from other sources of cosmic microwave background patterns, including gravitational lensing by cosmic structure, contamination from galactic emissions, and systematic instrumental effects. Advanced analysis pipelines must account for all these conventional sources while maintaining sensitivity to the subtle signatures that might indicate interdimensional interactions. Dr. Stephen Feeney from Imperial College London has conducted extensive searches for universe bubble collision signatures in Planck cosmic microwave background data. His analysis has identified several candidate signals that show patterns consistent with theoretical predictions for parallel universe interactions, though the statistical significance remains below the threshold required for definitive detection. These tantalizing hints suggest that more sensitive future observations might reveal clear evidence for interdimensional collisions. The cosmic microwave background also preserves information about the fundamental physics operating during cosmic inflation, potentially including evidence for the quantum processes that create parallel universe branches. If the many worlds interpretation of quantum mechanics applies to cosmic inflation, different quantum outcomes during inflation should create parallel universe branches with slightly different cosmic microwave background patterns. Professor Andreas Albrecht from UC Davis has explored how quantum fluctuations during inflation might create cosmic microwave background patterns that encode information about parallel quantum branches. These patterns would appear as subtle non-Gaussianity deviations from the simple random pattern expected if inflation involved only classical physics processes. Detecting these quantum signatures could provide the first observational evidence for quantum parallel universes operating on cosmic scales. The search for parallel universe signatures also involves looking for evidence of extra-dimensional physics that might influence cosmic microwave background patterns. If our universe exists within higher dimensional space, gravitational effects from parallel universe regions might create systematic modifications to cosmic microwave background temperature patterns that could be detected through precision analysis. Dr. Latham Boyle from the Perimeter Institute has investigated how the cosmic microwave background might contain information about the topology of extra-dimensional space and the distribution of parallel universes within higher dimensional regions. Different extra-dimensional geometries would create distinctive patterns in cosmic microwave background polarization and temperature correlations that could be distinguished through advanced analysis techniques. Future cosmic microwave background missions will provide the sensitivity needed to definitively detect or rule out many theoretical predictions for parallel universe signatures. The proposed LIGHT-BRD mission would measure cosmic microwave background polarization with precision sufficient to detect universe bubble collision signatures that remain below current detection thresholds. The analysis of cosmic microwave background data for parallel universe signatures also involves sophisticated statistical techniques that can quantify the probability that observed patterns result from interdimensional interactions rather than random chance or systematic effects. Bayesian analysis frameworks compare theoretical predictions for different types of parallel universe interactions against observational data to determine which models best explain any detected patterns. Professor Dragan Huterer from the University of Michigan has developed techniques for combining cosmic microwave background observations with other cosmological data sets to search for correlated signatures of parallel universe interactions. These multi-messenger approaches could detect interdimensional effects that would be unobservable through cosmic microwave background analysis alone. The cosmic microwave background preserves information not only about universe bubble collisions, but also about any primordial gravitational waves that might have propagated from parallel universe regions during cosmic inflation. These gravitational wave signatures would appear as distinctive patterns in cosmic microwave background polarization that could reveal information about the structure of extra-dimensional space and the dynamics of parallel universe interactions. Dr. Eli Kavitz from Ben-Gurion University has explored how cosmic microwave background observations might detect signatures of eternal inflation, the theoretical process where cosmic inflation continues forever in some regions while ending in others, creating an infinite multiverse of universe bubbles. Different models of eternal inflation make specific predictions for cosmic microwave background patterns that could be tested through advanced observational programs. The search for parallel universe signatures in cosmic microwave background data also involves looking for evidence of symmetry breaking that might occur when universe bubbles with different physical constants interact. These interactions could create temperature patterns that encode information about the fundamental constants operating in parallel universe regions, potentially revealing whether physical laws vary between different cosmic domains. Advanced computational techniques are required to process the enormous datasets created by cosmic microwave background observations, while maintaining sensitivity to the subtle patterns that might indicate parallel universe interactions. High-performance computing systems analyze millions of temperature and polarization measurements to extract statistical patterns that could reveal interdimensional signatures hidden within cosmic noise. The integration of cosmic microwave background analysis with theoretical developments in string theory and extra-dimensional physics provides additional opportunities for detecting parallel universe signatures. As theoretical models become more precise in their predictions for how parallel universes might influence cosmic microwave background patterns, observational searches can become more targeted and sensitive. Professor Mark Kamienkovsky from Johns Hopkins University has investigated how future cosmic microwave background observations combined with gravitational wave detections might provide definitive evidence for parallel universe interactions by detecting correlated signatures in both cosmic background radiation and spacetime distortions. Such multi-messenger detection would provide compelling evidence for interdimensional physics operating on cosmic scales. The cosmic microwave background represents our most direct observational window into the earliest epochs of cosmic history, potentially preserving evidence for parallel universe interactions that occurred during the first fraction of a second after the Big Bang. As analysis techniques continue advancing and future space missions provide even more sensitive observations, the cosmic microwave background might soon reveal whether our universe is truly isolated or whether it exists within a vast multiverse of interacting parallel realities. Chapter 4. Particle collisions, high energy. Particle collisions at the world's most powerful accelerators might provide direct access to parallel universe interactions by creating conditions where particles from our universe could briefly tunnel into extra-dimensional space and potentially interact with matter from parallel cosmic regions. The extreme energies achieved in modern particle accelerators approach scales where theoretical models predict that the barriers between parallel universes might become permeable to certain types of particles. The theoretical foundation for particle collision detection of parallel universes emerged from extra-dimensional theories developed by physicists like Lisa Randall and Raymond Sundram, who showed that our universe might exist as a three-dimensional slice through higher dimensional space containing other three-dimensional universe regions. At sufficiently high energies, particles might gain enough energy to escape our three-dimensional space and propagate through extra-dimensional regions where they could interact with parallel universes. Dr. Savas Dimopoulos from Stanford University has calculated that particle collisions at energies approaching the Planck scale, where quantum gravity effects become important, might create microscopic black holes that could serve as portals between parallel universe regions. These quantum black holes would exist for extraordinarily brief periods, but might allow particles to tunnel between different cosmic domains before evaporating through Hawking radiation. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, creates collision energies up to 13 trillion electron volts, still far below the Planck scale, but approaching energy ranges where extra-dimensional effects might become detectable. Dr. Michelangelo Mangano from CERN has designed search strategies for detecting particles that disappear from our universe during collisions, potentially indicating escape into extra-dimensional space. The experimental signature for parallel universe interactions in particle collisions would involve missing energy and momentum that cannot be accounted for by any particles detected in our universe. If particles escape into parallel universe regions during collisions, they would carry away energy and momentum that would appear as unexplained imbalances in the collision debris, assuming perfect detector coverage and accounting for all known particles, including neutrinos. Professor John Ellis from King's College London has explored how particle collision experiments might detect gravitons, the hypothetical particles that mediate gravitational interactions escaping into extra-dimensional space. Unlike other fundamental forces that are confined to our three-dimensional space, gravity might propagate through higher dimensional regions, allowing gravitons to serve as messengers between parallel universes. The search for parallel universe signatures in particle collision data requires sophisticated analysis techniques that can distinguish genuine interdimensional effects from instrumental backgrounds, detector inefficiencies, and unknown particle physics processes. Advanced machine learning algorithms analyze millions of collision events to identify patterns that might indicate particle escape into parallel cosmic regions. Dr. Maria Spirapoulou from Caltech has developed experimental protocols for detecting large extra dimensions through their effects on particle collision products. If our universe exists within higher dimensional space, with dimensions large enough to affect particle physics, processes high-energy collisions might create particles that propagate through these extra dimensions and return to our space at different locations, creating distinctive signatures in detector systems. The upcoming high-luminosity Large Hadron Collider upgrade will increase collision rates by an order of magnitude, potentially providing the statistical sensitivity needed to detect rare interdimensional particle interactions. Dr. Gian Giudici from CERN has calculated that even if parallel universe interactions occur in only one collision per billion, the upgraded LHC might accumulate sufficient data to detect these extraordinary events. Future particle accelerators, like the proposed Future Circular Collider, could reach energies 7 times higher than the LHC, approaching energy scales where theoretical models predict that interdimensional effects should become clearly observable. These machines would create collision energies comparable to those that existed during the first instance of cosmic inflation, potentially reproducing conditions where parallel universe interactions naturally occur. The detection of parallel universe signatures in particle collisions could also involve searching for exotic particles that can only exist in higher dimensional space that occasionally manifest in our three-dimensional universe through quantum tunneling effects. Dr. Arkaniham Nima from the Institute for Advanced Study has outlined theoretical frameworks where such extra-dimensional particles would create distinctive decay signatures unlike any particles confined to our space. The analysis challenges for parallel universe particle collision detection involve distinguishing genuine interdimensional effects from new particle physics phenomena that operate within our own universe. The discovery of previously unknown particles or forces could create signatures that mimic parallel universe interactions, requiring careful theoretical analysis to determine the correct interpretation of any unusual experimental observations. Professor Raman Sundram from the University of Maryland has investigated how particle collision experiments might detect warped extra dimensions, where the geometry of higher dimensional space creates regions with different gravitational field strengths. Particles propagating through such regions would experience time dilation effects that could be detected through precision timing measurements of collision products. The integration of particle collision searches with astronomical observations provides additional opportunities for detecting parallel universe interactions. If particles can escape our universe through high-energy collisions, similar processes might occur naturally in extreme astrophysical environments like black hole horizons, neutron star surfaces, or cosmic ray interactions in interstellar space. Dr. Luis Ankerdokwi from Lehman College has explored how ultra-high-energy cosmic ray interactions in Earth's atmosphere might provide natural laboratories for studying interdimensional particle physics. These interactions achieve energies far beyond any terrestrial accelerator and might create conditions where parallel universe interactions become observable through careful analysis of cosmic ray shower patterns. The search for parallel universe signatures also involves looking for violations of energy and momentum conservation that could indicate particle escape into extra-dimensional space. Advanced detector systems measure the energy and momentum of all particles produced in collisions with extraordinary precision, allowing researchers to identify events where these fundamental conservation laws appear to be violated. Professor Andreas Ringwald from the German electron synchrotron has investigated how particle accelerator searches for parallel universes could be combined with laboratory experiments that probe macroscopic extra-dimensional effects. These complementary approaches might detect interdimensional physics operating across different energy and length scales, providing more complete understanding of parallel universe interactions. The development of quantum field theory descriptions for parallel universe particle interactions represents an active area of theoretical research. These frameworks must account for how particles behave when they tunnel between cosmic regions with potentially different physical constants, vacuum energies, and spacetime geometries, a challenge that pushes quantum field theory beyond its traditional applications. Dr. Georgi Valley from New York University has explored how particle collision experiments might create virtual extra dimensions through quantum fluctuations that briefly open portals to parallel universe regions. These quantum tunneling events would be extraordinarily rare, but might become detectable through precision measurements of particle collision products and their quantum interference patterns. The search for parallel universe interactions in particle collisions also involves investigating whether certain types of particles might be universal in the sense that they can propagate freely between different cosmic regions. Gravitons, axions, and sterile neutrinos represent candidate particles that might serve as interdimensional messengers carrying information between parallel universes. Modern particle detectors achieve remarkable sensitivity to rare processes, measuring particle properties with precision approaching fundamental quantum limits. These capabilities are essential for detecting parallel universe interactions that might occur with probabilities measured in parts per trillion or smaller. Advanced trigger systems identify potentially interesting collision events in real time among the billions of mundane interactions that occur each second. As particle accelerator technology continues advancing toward higher energies and greater precision, the search for parallel universe interactions represents one of the most ambitious frontiers in experimental physics. Success would not only confirm theoretical predictions about extra-dimensional space, but would open entirely new approaches to studying the multiverse through controlled laboratory experiments rather than purely astronomical observations. Chapter 5. Quantum Computing. Quantum computing might provide the most direct experimental access to parallel universe interactions by creating quantum systems that naturally explore multiple computational paths simultaneously across parallel quantum realities. Unlike classical computers that perform calculations sequentially using definite bit states, quantum computers exploit quantum superposition to perform many calculations in parallel, potentially accessing the computational power of parallel quantum branches to solve problems that are intractable using purely classical approaches. The theoretical foundation for quantum computing as a parallel universe detection method emerged from David Deutsch's groundbreaking work at Oxford University, showing that quantum computers can only be understood by assuming they access parallel quantum realities during their calculations. Deutsch demonstrated that when a quantum computer factors large numbers using Shor's algorithm, it must be performing the vast majority of calculations in parallel quantum branches that remain inaccessible to direct observation. Dr. Scott Aronson from the University of Texas has explored the quantum computational complexity implications of parallel universe access, showing that quantum computers can solve certain problems exponentially faster than classical computers only if they can harness computational resources that extend beyond our single observed reality. The quantum speedups achieved by quantum algorithms require parallel processing across exponentially many quantum branches. The experimental approach involves designing quantum computing systems that can detect subtle signatures of parallel quantum branch interactions during their calculations. These signatures might appear as quantum interference patterns that exceed what is possible if quantum computers operate within a single quantum branch, or as computational results that indicate access to information not present in our observed quantum state. Professor Seth Lloyd from MIT has developed quantum computing protocols specifically designed to test many worlds interpretations of quantum mechanics by creating quantum algorithms that would produce different results depending on whether parallel quantum branches exist and interact. These algorithms use quantum error correction techniques to maintain coherence long enough for interdimensional effects to become measurable. The detection challenge involves distinguishing genuine parallel universe signatures from quantum decoherence effects, systematic errors in quantum hardware, and classical computational processes that might mimic quantum speedups. Advanced quantum error correction protocols are required to ensure that observed effects truly result from parallel branch interactions rather than environmental interference or technical limitations. Dr. John Preskill from Caltech has outlined quantum advantage, experiments that could demonstrate quantum computers accessing computational resources beyond what is available in our single universe. These experiments involve quantum simulations of complex many-body quantum systems that would require more computational power than exists in all the classical computers that could theoretically be built within our observable universe. The quantum supremacy milestone achieved by Google as quantum computer in 2019 might represent the first indirect evidence for quantum computing access to parallel realities. The quantum processor performed a calculation in 200 seconds that would require the world's most powerful supercomputer thousands of years to complete, suggesting computational capabilities that extend beyond classical physics operating within a single universe. Professor Shohini Ghosh from Wilfrid Laurier University has investigated how quantum computing systems might detect quantum interference between parallel computational branches by measuring correlations between quantum computation results that exceed classical limits. These correlations would indicate that quantum computers are accessing information from parallel quantum realities during their calculations. The development of fault-tolerant quantum computers with millions of quantum bits represents the technological frontier needed for definitive parallel universe detection through quantum computation. Current quantum computers operate with dozens to hundreds of quantum bits and are limited by decoherence times too short for complex interdimensional experiments. Future systems with longer coherence times could maintain quantum superposition long enough for parallel branch effects to become clearly measurable. Dr. Ignacio Sirek from the Max Planck Institute has developed quantum simulation protocols that could reveal parallel universe interactions by creating quantum systems that evolve according to the many worlds interpretation while remaining isolated from environmental decoherence. These quantum simulators would create controlled laboratory analogs of cosmic quantum processes that might naturally access parallel quantum branches. The quantum computing approach to parallel universe detection also involves searching for computational results that violate Church-Turing thesis constraints on classical computation. If quantum computers can solve problems that are fundamentally impossible for classical computers, this might indicate access to computational resources that exist across multiple parallel quantum realities. Professor Dorota Haranov from Hebrew University has explored how quantum computing systems might exploit quantum parallelism across many worlds' quantum branches to perform calculations that would otherwise be impossible. These calculations would involve quantum algorithms that can only produce correct results if they access information from quantum states that exist in parallel realities. The integration of quantum computing with quantum communication protocols provides additional opportunities for detecting parallel universe interactions. Quantum communication systems that achieve information transmission rates exceeding classical limits might indicate access to quantum information channels that propagate through parallel quantum branches. Dr. Charles Bennett from IBM has investigated how quantum cryptography protocols might reveal parallel universe interactions by detecting quantum information that appears to propagate faster than light or through channels that don't exist in classical spacetime. These effects would indicate quantum communication pathways that operate through parallel quantum realities. The search for parallel universe signatures in quantum computing also involves investigating whether quantum computers can access quantum memories from previous quantum computations that should have been erased by quantum measurement. If parallel quantum branches preserve information that becomes inaccessible in our branch, quantum computers might be able to retrieve this information through carefully designed quantum algorithms. Professor Daniel Gottsman from the Institute for Quantum Computing has developed theoretical frameworks for distinguishing genuine parallel universe effects in quantum computation from experimental artifacts or unknown quantum mechanical phenomena. These frameworks require multiple independent quantum computing approaches that would all show consistent signatures. If parallel quantum realities exist,